Class 10th Physics, chapter Magnetic Effects of Current. So previously we have seen the basic concepts about magnets and magnetic field and some related topics. Okay, so now we will get into the main part, which is magnetic effect of current. Okay, so what is the relation between current and magnetic effect? So for that, first see this demonstration.
Another experiment. So we have a switch, a copper wire, and a compass. Now we insert this in the switch and we'll see the activities. So we saw that when the circuit was complete, the needle of the compass started deflecting. So hence we can conclude that a current carrying conductor produces a magnetic field, and where there is current, there is a magnetic field produced by the current.
Alright, so in the demonstration there was a current carrying wire, some current was there. When there was no current and a compass needle was placed nearby it, so it was showing its usual direction, but when current was switched on, it has shown some deflection. And in which way it will deflect, that is again long explanation for that. There's a certain rule for it. I'm not covering it here because it is beyond the syllabus, and I will cover it in other video. So sometimes people refer it to snow rule, and I'm not going into details of it. Okay, but the most important thing is when there was no current, magnetic needle was showing its usual orientation due to Earth's magnetic field. And when current is switched on, then it shows a certain deflection, as if there is some magnetic material. Remember one thing, other than iron, nickel, cobalt, there are some alloys which are magnetic material, which shows some deflection. Even aluminium, which is not perfectly a magnetic material, it is called paramagnetic material. In high magnetic fields, it also shows some magnetic effect. Anyway, again, it is beyond our syllabus. So I want to say that copper is diamagnetic. It is not a magnetic material. In fact, it opposes magnetic field. That's surprising. So this deflection is not because of copper, but because of current, which is flowing through the wire. It means current has something to do with magnetism. We know when current flows, it produces, it gives some heating effect, but also it produces some magnetic effect. It creates some magnetic field around it. What is current? Flow of electrons. And casually, if we see it casually, it is more, we can say, flow of charge. It means flow of charge create magnetism. Often students ask me, from where these magnets have that magnetic property? What is the reason for that? Here is the reason. Oh, charge. Okay, here is the reason. Flowing or moving charge produces magnetic field. Why? Okay, well, we know that a charge has electric field. It has some electrostatics. That is why like charges repel, unlike charges attract. But other than that, there's another effect. If a charge moves, we know that the proton generally bound to the nucleus and they do not move. But let us suppose if it move, in fact, a nucleus moves, then it produces a magnetic field in a well-defined manner like this. I'll come to this later on. Why in this way? There is just, I'm discussing about rules, not getting into the deeper explanation, because again, these are far beyond our syllabus. So I want to stick with this only. Okay. With negative charge, if they are also moving along same direction as positive charge, the only direction, the curl of magnetic field. See, if it is going straight, magnetic field is in the form of curled, circular form. Later on, I will cover a certain law about it. Now, okay, once again, as you have seen in the demo, so I want to conclude it here also. Actually, what happened earlier, when magnetic effects were very much familiar, with physics societies. So there was a scientist called Oersted. So he performed an experiment, Oersted experiment. Not so important as in the perspective of exams, but for your own interest, it is very much of very much importance. Okay, so in Oersted experiment, there was a cell connecting some switch, and there's a wire, and as I shown here, so also I'm doing it here. So when there was no current, key was opened, uh, needle was showing its usual direction, but when key was closed, then there was current started to flow through the circuit, and there was a deflection. Uh, some people will say this time I deflected it this way. Actually, there are so many situations related to this. If I place this compass needle over the wire, deflection would be different. If under the wire, deflection would be different. On one of the side, then it would be different. On other one of the side, then it would be different. The bottom line is, ultimately, I want to show a deflection only. Nothing more, nothing less. Just the deflection, which I'm showing here. So, what were the Oersted observations? So he observed if current flows, compass needle shows deflection. Second, if current is increased, deflection also increases. What does it mean? It means that flowing current produces magnetic field, and amount of current is, we can say, directly proportional, or in some way, as current is increasing, magnetic field also increases. So that was Oersted's experiment. And remember, in order to find converse of this, means from magnetic field can we produce current, Faraday worked a lot, but we will cover that in upcoming videos. Okay, now the thing is, okay, we know about Oersted experiment, and we have come to know about this entire this scenario that current flows and it produces magnetic field. So we are done with it. But what is the nature of magnetic field produced by a current carrying wire? This is the big question. So for that we have a rule. I wouldn't say it is a law. It is not a law, but it is more precisely we can say it is a rule. So it is Maxwell's right hand thumb rule. Some people say it Maxwell's right hand thumb law. I have no issues with any of the name. So many cricket lovers know Maxwell as Glenn Maxwell, Australian player, but and I think he is right-hander. So okay, first I would like to draw a hand. Of course, right hand. That's enough. I can make more fingers, but that's enough, I think. So now, let us suppose, okay, if outstretched thumb of right hand shows the direction of current, then curl of the fingers will show the direction of magnetic field. By the way, symbol for magnetic field is B. Okay, what does it mean? First, just state the law. So here it is. If outstretched thumb of right hand shows the direction of current or motion of positive charge, that is important. Then curl of the fingers will show. So if outstretched thumb of right hand shows the direction of current or motion of positive charge, that's important. Then curl of the fingers will show the direction of magnetic field produced by the current or moving positive charge. This law is applicable for positive charge only, and we know that direction of current is supposed as motion along the motion of positive charge. So remember, no need to get confused. Current, so magnetic field. Positive charge, so magnetic field or positive charge. Some people would say that actually current flows due to electron, motion of electron. Yeah, of course, but we take the direction of current opposite to the direction of motion of electron. It means if electrons are flowing this way, means negative charge is flowing this way, then current is flowing that way, and that is why magnetic field going along the direction of curl of the finger. Or positive charge is going, then there's no problem with positive charge. So um, just keep this thing in your mind, that if such question comes, keep this thing in your mind, whether positive charge is given, current is given, or negative charge is given. Now, how are we going to apply this rule uh, and which type of question would be asked? But before that, uh, let me introduce another topic: magnetic field due to straight current carrying conductor. All right, so straight current carrying conductor. If this is a straight current carrying conductor carrying I current going vertically upward, then the direction of magnetic field due to this wire will be this way. In fact, I want to make a thicker wire so that you people will not get confused about the, because this is a 3D diagram, and 3D diagram often confuses a student or a reader with its illustrations. So now you can see it here. Now if we hold this wire this way and thumb is pointing along the direction of current, then curl of the fingers will show the direction of magnetic field produced by it, like this. Okay, so another one here, another one here. But what about this point? What will the magnetic field here? What will the magnetic field here? And so on and so forth. So remember one thing. Near the wire, we have to draw magnetic field line close, which shows a stronger field. See, it is showing a stronger field. But as we move away from the wire, we have to show that the gap between these magnetic field line increases even more. So remember in the previous video I discussed about it, that if field lines are closer to each other, it shows stronger field, and field lines are away from each other or rarer in that region shows weaker field. So here, as we move away from the wire, we receive weaker field. Now there are some properties. Okay, there's no theory about this magnetic field produced by a straight current carrying conductor. Just property. We have to just understand what properties its magnetic field produced by this wire have. So properties. Magnetic field lines are actually produced by this straight conductor are concentric circles. I have to change. Actually, I often do this thing. Okay, magnetic field lines are concentric circles. Field lines are denser near the wire, showing stronger field. And rarer as we move away, showing weaker field. In fact, remember this thing. Magnetic field, you remember this symbol. Magnetic field due to straight wire is inversely proportional to, sorry, distance. It is not the radius. You can say radius, but it is the distance. As we move away from the wire, R increases, but B decreases. Remember this relation. No numerical from this chapter, but you have to understand these things. Third, if current is increased, magnetic field also increases. B, due to this wire, is directly proportional to current flowing through the wire. तो अगर आप current double कर दोगे, if you will double the current, then magnetic field also get doubled. Next, if current is reversed, B also get reversed. And this is understandably, we can say, why is it happening? Because of this right hand thumb rule. How is it so? So what I am going to do is, all right, these are four different diagrams, and in first, okay, this is current going up, current going down, current coming out of the plane of the paper, current going into the plane of the paper. Now, if I apply that Maxwell right hand thumb rule, then there's current going upward like this, and curl of the finger going here behind and coming in front. So it is going this way, coming out that way, and here it is. You can draw a few more, and if we go away from the wire, these will be going far from each other, showing weaker field. I'm not showing it here. Now, like this, fingers are coming out from the right side, going in to the left side, like this. So if we reverse the direction of current, then direction of magnetic field also get reversed. Now see, this type of dot often used as something that is coming out, whether it is field line, whether it is direction of force, whether it is current. So right now it is current. It is coming out of the plane of the paper. So if I grip this current, this is the curl of the fingers going like this. You can see concentric, making wire as a center. Okay, you can see this is the wire, and if it is coming out, you will see a dot only. So that is why. So curl of the finger will go like this. More. One more. And here, this X, or we can say cross, actually current, if current is going downward, you can see this flat surface only, but they mark it as cross, and like this. Actually, this cross is due to special screws which has this cross sign on them, if you could remember. It is like this. So if we see this side coming toward us, we'll see dot, and if it is going away from us, we will see cross. So this is the idea behind this. But now, if I grip it, current is going downward, like this thumb is going downward, then curl of the finger is going this way, clockwise way. See, you don't need to memorize these, just use thumb and curl of the fingers only. You have to align that thumb along the direction of current only. This. That's all. Now let us suppose we have a proton which is going up. Will it produce a magnetic field? Of course, because proton carries positive charge. And in which way will it produce magnetic field? So the answer is in the same way. Positive charge moving up, we will grip it, and magnetic field will look like this. And same here, but in, okay, so it means current, oh my god, I didn't mention it, and green is magnetic field here, and also here, and also here, and also here. Here, P, positive charge velocity, its motion is, I'm showing it with green mark, and with red, I'm showing magnetic field. So in all the cases. So it means a positive charge and a current, if in a question, a current is given or a positive charge motion is given, you can directly apply Maxwell right hand thumb rule, and there's no problem about it. proton is coming out, so uh, this will be the direction of magnetic field. If going inward, then this will be the direction of magnetic field. But what if electron is moving in such a way? So in that case, first assign what will be the direction of positive charge or what will be the direction of current in such a situation. So opposite to the electron, we assume the direction of current. This is the direction of current. This is the direction of current, and this is the direction of current. So in such a situation, if current is going downward like this, so curl of the finger will go like this. Then corresponding current will be in upward direction. So curl of the finger will go like this. And if electron is going upward, then corresponding current will go downward like this. So curl of the finger will be in clockwise direction, and here I am directly doing it in anti-clockwise manner. So this is how the question will be asked, and you have to be aware about it. Now a task for you. So more videos to come. Stay connected.